Hello and welcome to the Daily Space for today, August 3rd, 2018. I am today's host, Dr. Pamela Gay, and I am here to put science in your brains. Now, it is a slow Friday when it comes to new news joining us on the internet, but I think this is overcompensated for by this morning's announcement that we have a new crew of astronauts who have been selected to train to fly to the International Space Station aboard the new, or fully tested and ready to go, I think is a better way to put it, Dragon capsule aboard the Falcon 9. This press release... Sorry, I have massive binging going on in the background. Let me see what I can do to stop the binging. There we go. Binging should now be stopped. Okay, so as some of you may have seen this morning during their press conference, which I'm afraid I wasn't able to share this morning, but during the press conference, a new group of astronauts was announced. This was a joint announcement between SpaceX and NASA, and now we wait for things to finally get rolling in terms of finalized launch dates, finalized, well, pretty much everything else. But having astronauts that can train is certainly the first step. One of the things that we have to always remember is every capsule is a little bit different. And that little bit different, means a whole lot more training. Now, with the commercial crew spacecraft, we have the Boeing Space ST-100 Starliner, Eric Boe, Chris Ferguson, Nicole Mann, Josh Cassanda, and Suri Williams. So this is a split gender crew, as is an awesome way to have things. We also have the Falcon crew, whose names I am trying to find, and unfortunately I inadvertently let my Twitter stream scroll on me. What I can tell you is all these astronauts are currently doing a AMA over on Reddit, and the other half of the selected astronauts are all, unfortunately, men. I say unfortunately because this leads to oddities of language. So there have currently been minor Twitter wars breaking out over people saying manned space flight instead of crewed space flight, C-R-E-W-E-D, not C-R-U-D-E, and instead of saying human space flight, in this land of wanting to make sure that we can inspire everyone in the next generation to see themselves as future space explorers. It is a kindness to open the door and allow people of every walk of life who have the skills the opportunity to compete and be fairly selected based on their skills and not based on any other characteristic. So currently we're looking at a selection of 5 individuals, which based on the photo includes 2 women and 1 man of color and a whole lot of, well, white guys. I have nothing against white guys. I am married to a perfectly good one. But again, it would be amazing if the faces going to space represented the full diversity of the faces that we have in our everyday population here on Earth. Anyways, moving on to more scientific topics, which is, after all, where I'd like to be. I have new science results, or at least newly processed images coming in. And thank you so much, Fenrig, for the subscription. That is awesome. This is Fenrig's second month in a row as a subscription. If we can light up the chat with all those rockets, it would be kind of amazing. So in the image that I show you here, we have what appears to be a diffuse cloud of white and blue, punctuated by some strands of red features. These strands of red features are actually supernova remnants. This particular supernova was first detected in 1966 in radio observations. It just doesn't stand out in images as saying, I am a supernova remnant. And the reason that it doesn't stand out is this particular supernova remnant is embedded in a variety of star-forming regions. These star-forming regions are what you see in white on this image. And those star-forming regions continue off the edge of this image for quite some distance. The star-forming regions are referred to as W3, 4, and 5 because astronomers can't give things interesting names. In this particular image, we're given the opportunity to see this supernova remnant as it appears to the Spitzer Space Telescope. It was observed in 2 different infrared frequencies that allowed us to see exactly how the shock waves from the supernova were compressing material in the surrounding interstellar medium, in those surrounding star-forming regions, and combining these observations with other observations in high energy light, gamma ray, and X-ray, as well as lower energy radio, we're able to get a better understanding of exactly how the supernova remnant has evolved over time. Now, this remnant is just 6,400 light years away. And one of the things I personally find interesting about this is we don't have a firm date for exactly when this particular star went boom. So we're looking at a remnant of unknown age and of amazing brightness, given its size spread out over the sky. And this is pointing out once again that supernova from young hot stars can go off in star-forming regions and do go off in star-forming regions. At some point in the future, we may be looking up at the Orion star-forming region and seeing new supernova going off there. Perhaps someday Orion's sword will, well, gather some bright red gems as it continues to hang from his waist stars, his belt stars. So this is kind of just a pretty picture showing us the capacity of all of these different telescopes to work together to bring us new science. Now here we have just flat out amazing new science. This is an artist's rendition of a rather horribly named object, and here I have to read my notes. This is SIMP J0136 5663 plus 0933473. While horribly named, this object is amazing with the science it has allowed us to do. Observed with a very large array, this particular object sits right at the cusp between being a giant gas planet and being a dwarf brown star. We know that this cutoff appears at about 13 times Jupiter's mass, and this object, as near as we can tell, is 12.7 times the mass of Jupiter. And this means it could have, it might not have, when it comes to the deuterium burning, the burning of a special heavy form of hydrogen that can occur at lower masses and lower temperatures than the normal hydrogen burning that occurs in stars like our own sun. When deuterium burning is the only form of nuclear reactions that can go on, an object is considered a brown dwarf, and it is only able to go through a short period of nuclear fusion in its core. Once the deuterium is burnt out, the star simply continues to sit there, now as a stellar remnant, cooling with time. Now, one of the amazing things about how these gassy objects appear is, even though this object is at least 12.7 times Jupiter's mass, it sorry, I'm losing my voice. It is only about 1.2 times larger in radius than Jupiter. As we pile more and more mass onto these borderline objects between gas giants and brown dwarf stars, the added mass causes them to contract faster than they grow with mass. So this means that while, yes, the object is slowly growing in radius, the density is growing faster than one might expect. Essentially, gravity is pulling the object together faster than the pressure laws are able to expand the gas outwards. So here we have an object that's just plain cool based on its physics. Now, this is where the VLA radio observations come into play. Any of you out there who want to can, well, basically hotwire a DirecTV dish to use it as a small radio telescope, and you'll be able to detect our own solar system's planet Jupiter as it emits light in the radio, largely through aurora and magnetic field interactions between Jupiter and its moon Io. These radio signals make Jupiter really stand out as a cool object to observe in our sky for backyard radio telescopes. Now, with SIMP, many numbers, the object that we're talking about today, that DirecTV dish isn't quite going to be able to do the job that's needed. But by using the multiple dishes that are part of the Very Large Array out in New Mexico, astronomers are able to observe this object and see that it too has amazing radio aurora. Exactly how you get these aurora in an isolated object that isn't interacting with stellar winds the way Jupiter is interacting with solar winds, and our own planet and many of the others in the solar system are interacting with solar winds. This is a big question mark. We hadn't anticipated finding isolated objects that are at this planetary brown dwarf size that would have this kind of aurora. By studying this object, we hope to be able to understand exactly how it is that stars and planets can generate their own magnetic fields. It's thought that maybe with this particular object, there are what you might either call planets or moons that are interacting and thus generating these aurora. This, again, is consistent with the interactions we see between Io and Jupiter. This is just plain a cool object that needs a whole lot more follow-up, and it's worth remembering SIMP J0136566 plus 0933473 as an object that you should keep track of if you're interested the way I am in trying to understand just what makes a star and what makes a planet, and how exactly these two kinds of objects are capable of generating powerful magnetic fields. Now, those are our primary stories for today, and this is your opportunity to start asking questions. Just please go ahead and @ me in the chat, and I'll answer what I can. While you're typing in those questions, I'd like to remind you that the Daily Space is brought to you every Monday through Friday, except on major holidays, right here on Twitch at 1 p.m. Eastern, 10 a.m. Pacific, 6 p.m. London time. We are a production of CosmoQuest, and you are invited to join us over on CosmoQuest.org and help us map out other worlds in our solar system. Right now, we're gearing up to do a presentation on Mercury in December, and we can use all the Mercury and Mars data you can send us. So please, if you have a spare moment, if you have some spare screen real estate, click over to CosmoQuest.org and do some science. CosmoQuest and the Daily Space are a multi-institutional collaboration. If you give us a follow, you will be able to keep up when all of our different faces go live, bringing you science right here on Twitch. In addition to the Daily Space, we also have Astro office hours brought to you Tuesday nights and Sunday afternoons by myself and by Annie Wilson, one of our planetarium crew. We also have Astronomy 101, which will be following directly after today's Daily Space. This comes to you from Dr. Matt at the Planetary Science Institute and his student, our coder, Jay Myers, Big J on Twitch. Big J knows his code. He's still learning his astronomy, and you can learn with him under the careful guidance of Dr. Matt. So give us a follow. Keep up with all of our faces as we go live. We are supported by you. Every subscription and every bit really helps. So thanks for coming, and now I'm looking to see what all you have in terms of questions. I see that Ironheart, sorry, I'm trying to move windows between screens. I see that Ironheart is asking, what would the magnetic field be reacting with to create aurora? Could it be cosmic rays? It's probably not cosmic rays. The flux of cosmic rays just isn't that high a density and sufficiently dense to form the kind of aurora that can be detected at a distance of 20 light years. So at that kind of a distance, and with the kind of detections that we're making, it's much more likely that the aurora are some sort of an interaction with a nearby moon or planet, depending on how this object eventually ends up being categorized. We see these kinds of interactions with Io. It is spewing various particles up into the space around it that can go ahead and get captured into a plasma stream that is connecting Io, which is thoroughly in Jupiter's magnetic field, and Jupiter. If there is a similar object to Io orbiting around this object, this gas giant or brown dwarf, it could, just as Io is responsible for some of Jupiter's aurora, that other object could be responsible for some of SIMP, many numbers, aurora. Lots of different things out there can cause all sorts of cool things to occur. And yeah, Hanny, it could even have rings. Or if it is a star, it could have a debris belt like our own asteroid belt. It's kind of wild how we rename things, whether an object is a star or a planet. If the rings of Saturn existed around our sun, it might be called the Kuiper belt or the asteroid belt. But because that debris belt is around Saturn, it's just called Saturn's rings. The physics scales in ways that our naming schema don't necessarily scale. So Hanny asked, would the interior of the object like this be metallic hydrogen like Jupiter or more starlight? So it comes down to where you're looking in the core. Yeah, there could be metallic hydrogen. There could be all the other things that we see in Jupiter's core. But in the center of all of that could be that deuterium that does the burning and the child particles that are formed during any nuclear reactions that might have occurred. So it won't be identical, but the physics is a continuum where as you add mass, you in a continuous way change how the interior behaves. So at this kind of a mass, you do see things that are similar to Jupiter, but it's a yes and. So yes, you see these things and you see these other things as well. Looking to see what else is in here. So Hanny, who is full of awesome questions today, also asked, wouldn't the biggest stars not make it out of the nursery before the sun-like stars had even gotten started? This can be true. Smaller stars do form slower than the largest stars, but because the largest stars are more rare, you can end up with stellar nurseries that don't necessarily have the most massive stars, the ones that end up, well, going boom the fastest. In this case, you can end up with the slower burn, the objects that will go supernova, but are going to go supernova a little bit later. And you can end up with some of the, not necessarily sun-sized, but larger stars, and perhaps in systems with truly not the largest stars existing. So these are the significantly smaller star-forming regions. You may even get sun-sized stars forming. Each stellar nursery is different, and the differences between the stellar nurseries are determined both by the initial mass, and thus the initial mass function of the stellar nursery. This is that probability of different sizes of stars forming, and also by the composition of the stellar nursery. So the composition also dictates exactly what size stars in what ratios you're going to end up getting in a stellar nursery. Now, the nice thing is, if you do have two systems of identical mass and identical composition, you will end up with the same probabilities of different kinds of stars forming. And while you might not get the exact same numbers of this mass compared to that mass, you do have predictable setups. Yeah, each system's a little bit different, but science helps us understand why it is we see all the things we see. So Noel asked about brown dwarfs. I need to go find his question. There's a lot of discussion about heartburn, and I know Larry was dealing with an actual fire in his complex this morning. I hope there's not much actual burning going on. Oh, Noel, I can't find your question. So if you could go ahead and re-ask it. There it is. Do brown dwarfs get prominences, and could the material in those prominences generate aurora when they return to the brown dwarf? About prominences, I'm not entirely sure. I just don't know the physics of the magnetic field well enough. What I do know is we don't essentially see the prominences on the sun falling back to interact with the sun's magnetic field. The prominences just sort of spew matter outwards. So here it's most likely going to be an interaction with something other than itself that is generating the aurora. So Fenrig is asking, if stellar nursery has lots of large stars that go supernova, does that mean it could contain relatively more black holes as well? Relatively is a complicated word. So the initial mass function doesn't vary hugely from one stellar nursery to another. What varies is if you have a probability of 1 in 500 stars is going to be this mass, and you only have 400 stars, you're probably not going to get that particular high mass object forming. There are slight variations in the stellar mass function on top of just the, if it's smaller, you're just not going to see as many of the rare stars. Now, if you have a particularly large star forming region, and if it has the correct composition to lead to a higher probability of massive stars forming. Yes, that in turn says you have a higher probability of stellar mass black holes also coming into existence in that particular system. So do we have any more questions? And I'd like to remind you all one more time that as soon as we're finished with the daily space, I will be handing this channel over to Dr. Matt and Big J, who are going to be coming back and doing Astro 101. Thank you, Trekker Kev, for the bits. Can we light up the chat with some rockets, please? Thank you so much. So Hanny is asking, wouldn't the biggest stars not make it out of the nursery before the sun-like stars had even gotten started? Well, they would have gotten started, but they wouldn't have gotten finished. But that's okay. I mean, that's essentially what we're seeing. Let me switch. Thank you, Keeper of Maps. Let's also light up the chat for Keeper of Maps. So here in this particular image, what we're seeing is the remnants of a supernova in a region with a variety of still star-forming areas. Now, clearly the star forming has started. I don't know how far it's progressed. I don't know exactly which of these star forming regions that supernova might have been tied to, or if it was tied to one that has already completed its star formation. It's complicated, I think, is the best answer. So yes, in some stellar nurseries, the biggest stars will have formed and died before the smallest stars have finished forming. But it will vary from system to system. I love the wings, Larry. And thank you for the heart, Uncle Bill. I hope I answered your question, Hanny. I'm not sure that I did. Initial mass functions are complicated. We're still working to fully understand them as we study open cluster and star forming region after open cluster and star forming region. So if there are no more questions, and thank you so much for the comment on last night's learning space. If you weren't able to tune in live last night to Learning Space, and apologies to all of you in Europe, because if you chose sleep, you didn't get to see the episode. This is a reminder when you miss things live, you can go ahead and check them out either over on YouTube, or if they haven't hit YouTube yet, they will still be in the videos here on Twitch. So if you miss us live, we're always here to watch in reruns. Fenring, I totally understand choosing sleep. And to the question of Dragon or Starliner, I have to admit that I'm going to choose the Dragon, mostly because the Falcon's already flying and SLS isn't quite as well tested at the moment. Basically, I'm too impatient. So yeah, we need more test launches. We need more rocket launches of the SLS before we can make a good decision on Starliner. Anyways, it has been fabulous to have all of you here. Adam, altogether, I'm determined to read your name as Adama because I'm a Battlestar Galactica fiend. So if I ever misname you, you now know why. Fellow Hoodlum, I hope you were able to catch last night's show because it was kind of designed for your time zone. So thank you all for being here. And this has been today's episode of The Daily Space. We will return on Monday. We will be here to put more science in your brain. If you still want to keep learning today, and I encourage you to keep learning every moment. Stay with the channel as we switch over to Astro 101. Give us a follow. We are sustained through your subscriptions and bits, and we are brought to you out of the Astronomical Society of the Pacific, working in collaboration with Youngstown State University and the Planetary Science Institute. Thank you so much for joining, and wherever you are in the world, have a fabulous morning, evening, or afternoon. And remember to get out and look up. Right now, Saturn and Mars are looking particularly glorious in the sky. So I will see you all on the other side. Bye-bye.